This video is on the objective calculate the test statistic or t-value. Right, so we're working with the student's t-distribution with so many degrees of freedom here. Right, and degrees of freedom for a hypothesis test for the differences of paired data. And again, you're seeing in parentheses after the words paired data, dependent samples. Okay, when you hear the words paired data, you should think dependent samples, because paired data is really two samples, but each pair of data is related to a single individual or are related to one particular object, as we'll see here. All right. So again, if you're unfamiliar with the topic, want to read more about it, see more about it, please click on More Instruction and look at their notes, their videos, their examples, and hopefully those help you out. Okay, so here a statistician believes that women received more bachelor's degrees than men last year. To test this claim, she selects colleges and universities randomly and compares the number of bachelor's degrees awarded to men and women. Find the test statistic and degrees of freedom for an appropriate hypothesis test using the data set below. Let the difference D for each university be computed as the number of degrees awarded to women minus and then degrees awarded to men. And it looks like on average, because I don't understand these numbers, 5.63. Okay. So looks like maybe the average for the school, like maybe for the departments at the school. We'll just assume that. Alright, assume that the numbers of degrees earned are normally distributed, and we're asked to round the test statistic to 3 decimal places. Alright, so I'm going to write this out, and I'll talk about what happens in general, okay, when we're doing these hypothesis tests for the the mean difference between paired data. Alright, so here's what's happening. Okay. You have, college number 1, college number 2, all the way down to college. In this case, I'll just say N. Right? I know that our list here has 7 rows in it. And for each of these colleges, they're recording 2 pieces of data. We'll call the first one, sample 1, which is the number of degrees awarded. It looks like, I'm going to guess it's like maybe on average per department, because these numbers don't make sense otherwise. So the degrees awarded to men, and then the second sample are again degrees awarded to women by these colleges. And again, the only way these numbers make any sense is if it's like maybe the average number of degrees awarded to women per department. Alright, so this first value is 4.58 for the college 1, and then the second value for the women is 5.63 for the first college. Then for the second college, it's 5.64 for the men and 6.15 for the women, and so on. All right. Now again, these 2 samples of values are definitely paired. Right? They're paired data. They're dependent samples. And the reason that is because you can't just switch values, right? These this pair of values is related to that first college, and I can't change those numbers with any other row. Same thing, this pair of data is related to the second college. All right, so what we're talking about here, when we have these paired datas, we're going to be looking at a third column, a column of differences. Okay, a column of differences. And those differences will usually be labeled by D, and what they want us to do in this example is take the number of degrees awarded to women minus the number of degrees. What's the difference between degrees awarded to women and degrees awarded to men at these colleges? Right. So let's say D1, the first difference is 5.63 minus 4.58, whatever that is. D2 is 6.15 minus 5.64, and so on, and I'd get down to Dn, right? I'd take this sample of n differences. Okay. And then once we have this sample of n differences, we're going to take the mean of this sample. Right, the mean of this sample, which is going to be called d bar, right? It's just like x bar, but it's the mean of all these differences. And we're also going to find the standard deviation of this sample of differences called S sub d. All right. Now, looking at this sample of differences, I'm going to go to the next page. We're going to apply the central limit theorem to this one sample of differences. Right. Since the population of the differences is assumed to be normal, right? The population of differences is assumed to be normally distributed, or it is normal. Or if the sample was large enough, if there were enough, about 30 or more of these differences, right? Or if the sample of differences was large enough, I'll say sample of diffs, right, for differences were greater than or equal to 30, right? Then by that central limit theorem we've seen for means, the distribution of these d bars, right, the distribution of the sample means would be a student's t distribution. And again, this is a student's t because I don't know sigma d. Right? We know the standard deviation for these sample differences, but we don't know sigma d. We don't know the population standard deviation. So that's why this is a student's t distribution. And the number of degrees of freedom, remember, this is now you're basically taking two samples and turning it into one sample. And you've done a one sample t-test before. Remember, the number of degrees of freedom was just the size of the sample minus 1. So with n minus 1 degrees of freedom. All right, sorry about the noise. I'm sure that there's some construction going on outside. And I really want to get this done, so I'm hoping it doesn't bother you too much. So remember, so there's n minus 1 degrees of freedom. All right. And the mean of these d bars, say mu sub d bar, is the mean of the population of all those differences. And usually this will be assumed to be 0 from the null hypothesis. All right. This assumption that mu d, the average of all the differences, is 0, this is usually going to be from the null hypothesis, this assumption. All right, and then the standard deviation of these d bars is, remember, it's usually sigma d. It would usually be sigma d divided by the square root of n, but we don't know sigma d as the student's t-distribution. Right? We're going to use s, our sample standard deviation, and then divide that by the square root of n. Right? And this might look familiar, right, when we worked with student's t-distribution and a single sample before. Right. So then our test statistic. For a test about mu d, a test about the mean difference for the population for all colleges, would be a t-score. Right? It's going to be a t-score. And it's going to be the sample mean that you got, right? The mean of this sample of differences is going to be d bar in the numerator minus mu d. But again, mu d, the population mean of the differences, that'll be assumed to be 0 in the null hypothesis. So you can write minus 0 if you want, but I'll just leave this as d bar in the numerator, divided by, and then this standard deviation of the distribution of the d bars, right? The sample standard deviation, SD, divided by the square root of n. Right. So I'll put minus 0. But, this is the mu d here, right? Really, it's just mu d. We might assume that mu d is something else, but for the most part, you're probably going to be assuming that mu d is 0. All right. Okay, so for this problem, I need to find all these differences, find their average, find their standard deviation, and then we can calculate our test statistic for a t-distribution with n minus 1 degrees of freedom, where again n is just the number of, basically the number of differences, right? N equals the number of pairs of data, which is the number of differences that you have in that sample of differences. All right, and I know this is a lot. All right, but let's watch me go through this here. All right, so here's the lists of data we are given. So I'm going to do this on the calculator. All right, I'm going to do this on the calculator. So I'm pulling up my TI-84, and 83 should be similar. And I'm going to enter these lists of data. So I go stat, edit, and then down list 1. I'll put all those numbers for the men, right? The average degrees awarded for colleges for the men, 4.58, 5.64. All right, and once I'm done entering, there are, 7 values here. I'm going to enter the other 7 for the women. I'm going to enter those down list L2. All right, and I'll be back when I'm done with those. They'll pop right up. Okay, so you can probably see now in my calculator I've got the lists written, the men's list and the women's list. So what I'm going to do now is, again, make a new list. So I move my cursor up to where it says L2, move over to L3, another list, an empty list, and I'm going to make a new list with all the differences between the values in L2, the women degrees, and all the values in L1. So I hit enter on L3 up there, and you see the cursor flashing. I'm just going to go second L2 minus second L1, and what's going to happen is it's going to take all these pairs of data, subtract the value from L2, take the value from L2 and subtract the value from L1. And you see all these now. List L3, this list L3 is all the differences between L2 values and L1 values. And L3, right, just keep that in mind, L3 is the list that I'm going to be using when I do my calculations. So now I want the mean of that list, L3, the mean difference, and I want the standard deviation of that, which you can calculate. Go stat, calc, right? Now it's just one list, right? So one var stats. You've seen this before. One variable stats. But remember, I want list L3, right? List L3. No frequency list, and then calculate. And this X bar is that D bar that I was mentioning, right? So pull up some paper here again. So on the calculator, I found D bar, the sample mean of all those differences, is 0.46. And then the standard deviation of all those differences, and pulling the calculator up, so that, now be careful, not sigma x, right? I want SX, S, the sample standard deviation. 0.410, let's go 447, 0.410447. And in fact, I'm not going to type this out. I'll show you how to use this SX as it is. All right, so now I have the mean of the sample differences, the standard deviation of the sample differences. Now there are, see, n is 7. There are 7 ordered pairs here. There are 7 differences. So the distribution of the d bars will be a student's t distribution with 6 degrees of freedom. All right, that's n minus 1, the number of pairs minus 1, or the number of differences minus 1. And again, this hopefully looks all familiar when you were doing a t-test with a single sample. And that's what we've done. We've taken 2 dependent samples with paired data and changed it, transformed it into a single sample of differences. And then, so working with this is exactly the same as before. All right, so now the test statistic. All right, what's the t-score of our sample mean? What's the t-score of our d bar? All right, so the test statistic is going to be 0.46 minus 0. We're going to be assuming that mu d is 0 here, divided by, and then 0.410447 divided by the square root of 7. All right, the standard deviation of the sample differences divided by the square root of the size of those sample differences. That sample differences sample. All right, and then they're asking us to round this to 3 decimal places, right? So what I'm going to do here, take 0.46, right? There was that d bar divided by, and then in parentheses, right? Because there's a whole nother fraction down here in parentheses. Now you can type this out, but if you just want to use the SD, the standard deviation of the sample, you can go variables, hit vars, go over to go down to statistics, number 5, and then you see SX there. That is the standard deviation I just had calculated. That's this 0.4104, 4104.469, whatever it was. And then divide that by the square root of the sample size, right? Divide that by the square root of 7. And there's our test statistic, all right? So our particular sample mean comes in at a t-score of approximately 2.965, right? Meaning that our sample mean is, almost 3 standard deviations above the mean of the population that we're assuming from the null hypothesis. And that's, usually when you're more than 2 standard deviations away, you're pretty far. So I'm going to say this is probably pretty far away and we would reject the null hypothesis, but we're not getting into all that yet. We're just asked to calculate the test statistic, right? And the degrees of freedom for our t distribution. But the process is the same every time, all right? We're going to see other problems when you have paired data. Take the differences. What's the mean of those differences? What's the standard deviation of those differences? Then you'll be looking at a t distribution with the number of differences minus 1 degrees of freedom, just like a single sample, right? You have a single sample of differences. And then your test statistic is just the t-score for your d bar. D bar minus the mean of the population d's, which is going to be usually assumed to be 0, divided by, and then the standard deviation of your sample divided by the square root of n, right? The square root of the number of differences. So we have 6 degrees of freedom, t-score of about 2.965. So let's enter that stuff in, right here. So t 2.965 degrees of freedom, 6. Great. All right, and again, they're going to take you through in the answer explanations, hopefully all the same calculations I did. Say, see again, they're taking the differences. All right. Oh, I guess these were in thousands. That's why they're writing them like this. I see. I see. Okay. So they're taking the differences, right? This is that list 3 that I had on my calculator, L3. See, the mean of those is 0.46. Again, the hypothesized population mean of the differences is 0. Usually, from again, from the null hypothesis, you'll be assuming this. The standard deviation is 0.410. N is 7. Right? There's 7 differences. And then, they found they just showed you SD. I'm just going to say use a calculator for that. Remember there was a formula to find the standard deviation for a sample. I'm not doing all that by hand. And the test statistic, again, 0.46 minus 0 divided by the standard deviation of the sample divided by the square root of the sample size, right? And they're coming back 2.968. Well, that's because they rounded. They rounded to 0.410. I used the whole thing, right? I used 0.410447, blah, blah, blah. They rounded their standard deviation, so that's why they're getting a little off here. I would suggest not to round until the very end. But if you're noticing that they're doing it in the answers, maybe you should, just to make sure you get the same answer they're getting. So it looks like they're rounding everything to 3 decimal places as they go through, which is kind of silly. You shouldn't do that, but for some reason they are. Alright, but hopefully the procedure made sense. Hopefully you could follow it. And I'll put up, of course, another video on this and do the same thing. Alright, so hopefully watching me do this, looking at more instruction, looking at the answer explanations when they come up. Hopefully all this stuff helps you when you're working on this junk on your own. Alright, and thank you very much for watching.